Hello, welcome to the explainer corresponding to the topic multi-level models. Before I start with this topic, I want to do a recap of the unit to put in context what we are going to do now and what's coming in the next few lectures. So we started the unit with the concept of causality, and which led us to the idea of causal models. So this is a relatively new thing in science, and not well known in psychology, but that is important to me because typically we use the statistical models when we want to do assertions about causality in the universe, and the statistical models are not appropriate for that. So we need to create those causal models that make sense. And then we use the probability realm of things in order to help understand, make predictions, and assist the causal models to make sense. So after that, we explore the issue of probability, because probability is the basis for all the analysis, and more importantly, or more specifically, to Bayesian statistics. So after probability, we looked at the linear model, and again, the linear model is at level up, but it's also the basis of a lot of analysis in statistics. So the t-test, ANOVA, regression, which are the most used analyses in psychology, they can all be re-expressed into a linear model. And after that, we went through the three strong, heavy classes on Bayesian statistics, and I think this is important because statistics is changing, not just in psychology, but in all disciplines, and statisticians are currently in a time of change, and I believe that Bayesian statistics will be the most important statistics in the future, and I think it's because I acquire knowledge in this area that would be very important for you to get this knowledge. It will give you an advantage over others who don't have this knowledge. So we are now going to pause from Bayesian statistics. We are going to return to a sort of traditional methods. The one today is not very traditional, it's multi-level approach. And the multi-level approach is very interesting. I'm going to go through now, and of course, if you watch the masterclass, you already know about it. And then in the next two lectures, we are going to use the concept of latent variables, which are part of factor analysis and structural equation modeling. And in the last week, we are going to do meta-analysis, and we return to this idea of traditional analysis and Bayesian analysis. So we are going to do traditional meta-analysis and Bayesian meta-analysis. Okay, so this is the recap of what we've done so far and what's coming in the last part of the unit. So let's dig into the multi-level modeling analysis. So first question: in which situations would you use multi-level modeling? So please, if you can, pause the video here, go to the masterclass and try to answer the question on your own, and otherwise, or in both cases, return and continue watching my answers. Okay, so the situations in which you use multi-level modeling is, in fact, you can use it for all analysis if you want it. Now, for situations in which there is the hierarchy of the data is just one level, we use the traditional analysis. But when we've got 2 levels or more, we didn't see more than 2 in the masterclass, but we can have more levels, then we need multi-level modeling. So these are the situations. But you are going to see that for the traditional approach, for situations in which we only have 1 level, so there is no hierarchy, typically we can use the multi-level modeling as well. So I'm going to go through that when we talk about further in other questions, when I answer other questions. So second question, what are the solutions proposed to deal with the issue of hierarchical data, and what are the benefits and disadvantages? Okay, try to answer by yourself and then return. So let's say a bit more about the different levels. So the typical example is, because this multi-level modeling comes from education research. Education research has to do studies with students in schools, and they are interested in the same variables that we are interested in psychology or in other areas, but applied to school. So when they have large data sets, they have, and for example, they want to investigate the relationship between the number of hours that they study, the students, and the academic achievement. Well, these are 2 variables. You can do a regression, or depending on the analysis, it would be regression or some other linear model. But the problem is that in order to do linear models, you need to have, there is an assumption of independence of the data. So each observation should be sort of a random experiment. So there shouldn't be, one observation should not be related to any of the other observations. And that is not the case when you have students that belong to one school and students that belong to another school. Then, and you may have different numbers, so some schools are bigger than others, and you may have different numbers of students belonging to different schools. So the participants that belong to one school, there are reasons to believe that their scores will be more similar to the scores of students that are in other schools, because they share definitely things that are not shared in the other students. They share some of the teachers. They share the region where the school is located, the average income of that region, etc., etc., etc. So we cannot assume independence of all the data points. So that is the need for multi-level modeling comes from. And now, solutions that were proposed. Yeah, one solution is ignore the problem and make and do the analysis, do a linear model, not considering the issue that there is not independence of data. And that's wrong. The benefit of that is that we keep the model simple, which is an advantage. Keeps the model simple. We don't want to do overfitting, but it's not correct. So second option is to average by school, but you can imagine that that's not a good idea either, because if you have, let's say, 1,000 observations in one school, 500 observations in another school, and 200 in another, and 100 in another, so you've got a huge data set there. But if you average per school, you've got 4 observations, and that is not something useful. You cannot use that data for anything. So averaging data is done typically when you have, let's say in this case, a lot of schools and not so many students in each school. But still, even if you do that, you are losing data because you're doing an average of a lot of observations and you lose that. And the other one is, well, we do the analysis in each school. And so we study the relationship between the variables we are interested in each school separately. And that sometimes is not possible because you don't have enough students in the school. Perhaps you have, I don't know, in some schools you have 3 participants. So in the case you've got a lot of schools and not too many participants per school, then doing the analysis within the school is not appropriate. And also, is it informative to do that? And also, you are doing, it's overfitting. You are doing a lot of analysis, a lot of parameter estimation. So that's where multi-level modeling comes, because it is out of the frustration of those problems with the hierarchical data. Okay, so what types of components do multi-level models have? And these are the random effects and the fixed effects. And so, but I also want to return to the idea of experimental data. So traditional analysis that are typically done at level 1, only one level of analysis, so we do the traditional linear models, can be done with multi-level approach. And that's the case of experimental data. So multi-level modeling doesn't come from the experimental literature. It comes from the more large samples, observational studies and questionnaire surveys. So here in psychology we do a lot of within subjects designs in which we give participants a lot of trials, and typically so we have either 2 extremes. One is the mathematical psychologists. So there are mathematical psychologists that they do models, fantastic mathematical models, to try that are targeted to specific experiments, and they even do it at the individual level or a combination of individual and a sample. And that's an approach, but that's not something that can be applied to everything. And the other approach is to do the averaging. So the solution that I mentioned before, the second solution, to average the trials in each condition in which the participant participates. So if participant 1 is, he or she may contribute to one condition or more than one condition. So let's say one condition, and so we say between subject study and participant 1 contributes to one of 2 conditions. But instead of having one trial, may have 50 trials. So typically in studies with reaction time, or in studies of accuracy in which you have very simple questions to answer. So let's say you've got 50 responses, but instead of using those 50 responses, an average is calculated for the participant, and that average is used. That's a lot of data. And I tell you, when I first started doing science in psychology, in the year 1998, I did my first analysis, and I started using SPSS, and I've had all this data, all the participants that had different trials, and then I had SPSS and I had to insert the data, and I said, how do I do it? I watched videos. Those days there were no many videos. I read the books of how to do the analysis, and basically I said, but where do I put all my data? And then I realized I had to get rid of the data. I had to take averages before putting the data in SPSS. And I thought that was outrageous. That was my first experience with data analysis. Now, I'm very glad now that with multi-level modeling that problem is solved, or with mathematical psychological models that I sometimes do. So that problem is solved. You don't get rid of any data. So instead of getting rid of all the trials that of each participant, what you can do is to consider participant as level 2 and observations as level 1. So basically observations are embedded in participants, right? So and it wouldn't be incorrect if we ignore that the observations belong to participants. So let's say we've got participant 1 with 50 observations, participant 2, 50 observations, and let's say 10 participants with 50 observations each. So we've got 500 observations, and we may be tempted to use all those 500 observations to do the analysis, and ignoring that they belong to different participants. So that's wrong because it violates independence, and that's why we can do multi-level analysis. Okay, so this is the digression that I had to do, but then let's return to what types of components multi-level models have, and we have the fixed effects and random effects. Random should be the idea of variability. And I tell you that the names that multi-level models received are, so sometimes these are called mixed models, hierarchical models, and there are other ways of being called. And the effects as well, random effects, but sometimes you don't call it effect, you call the variable components of the model and the fixed components of the model. Unfortunately, there is no agreement of using one way of calling things in this approach. Okay, so what's the essence? That's the important thing. Doesn't matter the names we give to things. What's the essence of the concept? Okay, so fixed components could be the slope of the regression, or it could be the intercept. So if, let's say we consider the two examples. Example 1, we've got students within schools. So level 1 is students, level 2 is schools. And in an experimental design, we've got observations and participants. Observations are level 1 and participants are level 2. Okay, so fixed effects. So the analysis we are doing, we've got a dependent variable and we've got an independent variable, and we have a regression. And it could be ANOVA as well, but it's a linear model, right? So what we do when we have a fixed effect, in the first example, that means that we've got a fixed intercept for the relationship between the independent variable and the dependent variable. So there is only one intercept. That's a fixed intercept. That means we don't care about the variability between schools in that intercept. There is one intercept for the whole sample. So that's a fixed effect. So let's continue with the intercept. If we have a random effect, we can calculate the variability of that parameter. So if it is the intercept, then how does the intercept vary among schools in example 1 and among participants in example 2? So that means that regression line, the intercept may be different in each school or different in each student. Now, you may think this is a bit of cheating, because this is one of the solutions that was proposed before. Let's do one regression line per school or one regression line per participant, and we are doing a lot of parameter estimation. Well, actually, it is not. No, it's not that. So we are not going to do different. We are not going to estimate different intersects and regression lines, but we are going to calculate, if we had to have a regression line, what is the most likely place for the intercept in each school or in each participant. So, and we have a distribution for that. And that distribution has to be as close as possible as as close as possible to all of these hypothetical intersects and hypothetical slopes. So instead of actually estimating the actual intercept for each school or for each student, for each participant, we have one, which is the central one, and a distribution that will accommodate for the other hypothetical intercepts. And what we are going to be interested in is in the standard deviation of that normal distribution. And in this, in the multi-level modeling tradition, we report the variance more than the standard deviation, but the idea is the same. Variance is the square of the standard deviation. So that is the random effect. We calculate the variability of a normal distribution with the mean in one intercept and a normal distribution which gives probabilities to where the individual hypothetical regression lines will be located. And we do the same with the slope. So for the slope, we have a point estimate slope that would be the best for all the schools or for all the participants according to the examples, and we've got a normal distribution that gives us a range of possible hypothetical slopes, but the exact slope is not part of the model. Okay, so there is one effect of doing this, that because the other slopes have to be in that normal distribution, values that are very far from the middle of the distribution are very, very unlikely. So for the model, those values will not be favored. So that what happens is what we call a shrinkage. So we are going to propose, intercepts that are closer to the mean than if we do the intercepts separately. And that's the big difference in multi-level and doing the analysis per school separately or per participant separately. If we do that, the intercepts will be further apart. Because we do the multi-level, the intercepts that we are going to propose are going to be closer to the mean. That's shrinkage, because the model will become more compact. Okay, so these are the two components, the random effects and the fixed effects. So let's go to the next question. Which approach is used to compare models? Well, we use the Bayesian information criterion, BIC, or archaic information criterion, AIC. And these values come from the log likelihood. What is the log likelihood? Okay, so remember, we saw this in linear models, that when we make a point estimate, that's the prediction of the model for each observation. So if we have 2,000 observations in one study, the model will make a prediction for each of these 2,000 observations. What's the prediction? Which form takes the prediction? It takes the form of a normal distribution or a t distribution, typically. And what we call the point estimate is the center of that distribution. But for the models, it doesn't say that it will be exactly that value. It could be values that are close, values that are close to that value that value will be very probable in the model, but still it could be values that are close enough, they still have some degree of probability. Anyway, so we use those normal distributions, and for each observation we will have a probability assigned to it. So what's the probability of observing that value in the model that we are proposing? So we've got one probability per observation. But we are interested in the whole model, not in the individual observation. So if we have 2,000 observations, we are not interested in each of the observations. So how about the model? How is the model predicting overall the 2,000 observations? Well, what we have to do is to multiply all these 2,000 probabilities that we obtain for each observation. That comes from probability theory, the multiplication rule. Now, this is uncomfortable to work with, because probabilities are values between 0 and 1. You start multiplying values that are lower than 1, 0.05 times 0.05, and the numbers become lower and lower and lower and lower. In order to avoid that, instead of using probabilities, we use the logarithm of the probabilities. That transforms the probabilities into negative values, and then the sum of the logarithms equals to the product of the probabilities. So when, instead of having to multiply 2,000 values, we have to add 2,000 values. And believe me, now today it's not a problem. We have computers doing this for us. But statisticians in the olden days, they needed shortcuts, and making multiplications is more complex than additions. So if you can do additions instead of multiplications, that's a benefit. So that's the log likelihood is the sum of the logarithms of the probabilities for each observation. And that is a negative value, and the more negative it is, the less probable are the observations in the model. So it will be a bad model if the probabilities are very low. Now, those numbers in itself don't mean anything, because it depends on the number of observations. If we have more observations, the value will be lower. Why? because you have to multiply low numbers more times, and it will be lower. Or add logs, and we will have more negative values. So that's why we need to do a model comparison. We established the log likelihood and what comes next, but then we have to compare to other models. In themselves, those numbers don't mean anything. Okay, so from log likelihood, we transform that into deviance, and just that the main reason of doing that is to deal with positive numbers instead of negative numbers. So we do -2 times the log likelihood. That gives us the deviance, and because we are multiplying two negative numbers, we get a positive number, and we multiply by 2, it just doubles the values. That and then remember, we need to deal with the other issue of, if we have complex models, we have to estimate more parameters, we can overfit the data, we need to avoid that, and in order to do that, we do a penalization. So BIC and AIC are statistics that use the deviance, and then they add points for extra parameters, and both use slightly different formulas with their advantages and disadvantages, but that's not the point of this course to discuss. And so we've got a BIC, and basically we are going to compare the BIC of one model to the BIC of another model. So, and here we've got 4 models with their BIC, and the question is, which of these models is better? The model with a BIC of 24, the one with 45, the one with 50, or the one with 58? And the answer is simple if you watch the masterclass. It's model 1 is the best here because it has the lower BIC. So the lower the BIC, the better the model. Okay, so this is important because I didn't pay much attention in the masterclass to this, and but I did mention this in the step-by-step guide for doing the analysis in JASP. But here we are going to spend a little bit more time on this. So how do you interpret the following differences between models? So first case, there is a model with an independent variable, which is a fixed effect intercept, versus a model without that independent variable. Okay, so let's say the BIC is lower in the first case. So the BIC is lower in the model with that includes that independent variable as a fixed effect intercept. What does it mean? Well, if the BIC is lower, that means that it's better than the other model. So it is better, the model that includes that variable is better than the model that doesn't include that variable. And that's how you interpret. You interpret that this variable is important for the model. Let's go to the second case. We've got a model with an independent variable, and we have a fixed effect slope. With that independent variable, but with a random effect slope. So basically, we add the variability in the second model. So for the slope, in the first case, we've got only the slope, and in the second case, we have the slope, but we also measure the variability of the slope among schools, first case, participants, second example. So let's say the BIC is lower in the first case, so in the one that doesn't have variability. How do we interpret that result? Well, it means that it doesn't make sense to add variability to that slope. That means that there is no differences among schools or there is no differences among participants in the slope. We are going to use only one slope for all schools in example 1 or for all participants in example 2. What happens if it's the other way around? The BIC is lower in the second model. Okay, so that means that adding variability to the slope is important. So that means that we should expect the slope to be different in either in the schools, example 1, or the participants, example 2. If there is variability in the slope, that means that the slope will be different. Okay? Now, third case, we've got a model with an independent variable, which is fixed effect intercept, versus a model with an independent variable that has a random effect intercept. So here we are talking about the intercept, not about the slope, and we've got one variable that in one model is fixed intercept, and in the other one we've got a random intercept. Let's consider that we've got a BIC lower in the fixed effect model. What does it mean? Well, it means that it doesn't make sense to add variability to the intercept. That means that the intercept will be the same in all the schools or in all the participants. What about the other way around? What if the model with a random effect intercept of that variable is lower? Well, in that case, it makes sense to add a random effect. So therefore, that means that the model assumes, and it is correct to assume, that the intercept will be different in each of the schools or participants.